Okay, so I'll talk about robust fitting of multiple models in computer vision. I'll start by explaining what I mean by that, and then the lecture will start by the basic approach, and then I'll show that there are many hidden assumptions which are not true in reality, and that we can improve, and then it will turn out also that the most difficult problem, multi-model fitting, will have some impact on the simplest problem. So I will just introduce the 4 problems I'll be talking about. The one that probably every one of you is familiar with is single class, single instance model fitting. So that's the first picture. You see some sort of points. There is one instance of the model, which is the line. You are trying to model the points as line on line, and the problem is finding the parameter of the line. We know the single instance means one line, and single model means that there's only one model I'm considering, which is a linear model, not a circle, not a parabola, nothing else. This doesn't work in computer vision almost ever. It works almost never because we always have outliers. Then we start considering robust single class, single instance fitting problem, where we have points which belong to the model, to the instance of the model, the single line, plus multiple outliers. Then we will go to single class, still only lines considered, and multiple instances, the 3 lines here. And then the final, most difficult one is multiple class, multiple instance fitting. So here the classes would be circles and lines, and the multiple instances are the different lines which you see in the picture. Now, of course, we don't do this because of lines and circles only, although one of the oldest computer vision papers still cited is that of the Hough patent from 1962, where people are interested in detecting trajectories in bubble chamber images. And we do this because we try to estimate the dipole geometry and then decompose it to rotation and translation of a camera so that we know the viewpoint, or infer the structure of a 3D set of points. We're modeling 3D scenes. We can do this for multiple motion segmentation. We have multiple cars, multiple structures in the 3D world, and you would like to detect each car separately, which means that all the points belonging to one rigid structure comply with a model of one instance of a fundamental matrix. Or we can interpret 3D data, like from a LiDAR, maybe in terms of planes, cylinders, and some other box-like objects. That's the bottom image. So modeling data is a very common problem in many areas. And this is a conference where we also have people who do human interfaces, so we can think about any 3 or 4 or 5, 6 variables that you have observations on, and you assume that there's some dependence, and the dependence has a parametric form. You can